Hello, AP Chemistry, and welcome to batteries and corrosion. We're just going to quickly talk about these sections from your guys' book for Chapter 20. So, first of all, what's a battery? Right, a battery is a self-contained redox reaction. Yes, self-contained, completely enclosed redox reaction from which we can get electrons to power something else, right? So if we look here, right, we have a flashlight, right, where we put our two batteries in series, right? We could get a combined voltage of 3, right? And it powers our flashlight and gives us light, yes? Or here we have an example of an alkaline battery, right? This could be any alkaline battery. They've set it up to look like one of the kinds you'd put in like a calculator or something. But anyway, alkaline battery, right? Again, self-contained. We have a negative end and a positive end where electrons flow out of the negative end, right? And back through the positive end, which again goes back to every single battery you've ever put into a device, right, has a negative end and a positive end. And if you don't put them in right, your device doesn't work, right? Because the electrons aren't flowing through whatever it is that they need to flow through, yeah? And here, this is an example of a car, right, lead sulfate or lead sulfuric acid battery, which is in most people's cars. And if we think about your car, right, yes, most of us do have combustion engines, right, which do actually make the vehicle go, but we also have a battery in there to help with all the electronic devices, right, which is why if you leave your lights on, right, that pulls from your battery, and then by the time you come back in the morning, your car is dead, right? And if we think about in general, right, that battery gets recharged, right? We would use it to run our lights, but it would recharge via the alternator while the car is moving. But that can't happen if your car is just running off its battery all night long. So anyway, but then we can recharge it, right, by connecting it to somebody else's battery, right, and jumping it, right? Which if we think, what does that really mean when we recharge a battery? What are we doing? Right. We are then basically switching the electrodes, pushing electrons through it, right, and forcing the reverse reaction to happen, right? Which means that we basically restart the reaction. Yeah? Make sense? Think about that and make sure it does. And here we have an example of what's this? Right, a fuel cell. And specifically, this is a hydrogen fuel cell, where what differentiates a fuel cell from a battery? Right, the self-contained nature, right? All of these are just grab and go, right? Fuel cells need an input of fuel in order to work, right? Just like, I don't know, can't think of anything. But we have to constantly have an input of H2 in order for this to produce a voltage. Yes? Does that make sense? All right, so these are some of the wonderful applications of electrochemistry to your everyday life, because without batteries, we would have far fewer toys. Okay, corrosion, another side effect of spontaneous electrochemical processes, right? Where here, what it's talking about is we have solid iron, okay, which then oxidizes, right? And if we think about what that means, right, oxidation means it becomes a more positive oxidation state, which means that instead of having solid iron, now we have iron ions, okay? And those iron ions, once they're oxidized, are then free to react with oxygen via redox processes to produce rust iron oxide, right? And what your book talks about is really neat, right? How we get the pitting, where the pitting is just the disappearing of my solid, right? And then we get the rust formation, right? Or where the oxidation occurs is separate from where the reduction occurs, right? And the reason that this happens is because the electrons can move through the metal, right? Which is why this is a unique thing for metals, right? As opposed to plastic, for example. If you can leave plastic stuff outside for a very, very long time, and it's never going to rust because it's not going to undergo these same reactions, right? Electrons aren't going to transfer through your plastic, right? To get this process to happen, right? If left outside forever, most plastic does get gross also via a different set of reactions. So anyway, here though, this is your zinc protection, right? Where if we put this layer of zinc on top, right, it says that zinc is more readily oxidized than iron, right? And if we think about what that means, right, zinc, iron, where's the iron reaction? Iron. Right? Zinc is more readily oxidized than iron. right? So if we look at my solids, zinc is more negative, which means that going in this direction, has a positive 0.76, this has a positive 0.44, right? Which means that this is more readily oxidized. Yeah, makes sense? All right, so since zinc is more readily oxidized, right, that is what's going to lose electrons, right? And then we'll get the traveling of my electrons, and we get our oxidation of just oxygen over here, right? Which then protects the iron, which means that we're not going to constantly lose our solid over time, right? We will eventually, right? Once all of this is used, right? Or if this pitting gets deep enough, then we'll also get some of our iron being used. But this helps to protect it and give it a much longer lifespan than it would have otherwise, right? What about copper? We use copper for a lot of things that live outside for really, really long periods of time. Why isn't that an issue? Right. If we go back to our table, right, if we look for copper, right, we see that the reduction of copper is spontaneous, which means that the oxidation of copper is, ding, 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 not spontaneous. Copper is not readily oxidized, right? It is slowly but surely over the course of time, right, like everything is susceptible to, with the right conditions. It can oxidize, right, which is that layer of green or bluish stuff that forms outside of copper metal stuff left outside. Think of the, right, Statue of Liberty or really, really old gross pennies, and that patina that forms, right? But if we think about that, that works kind of like this also, right, where that forms a layer on top, right, such that the actual metal underneath stays protected. Yeah, does that make sense? All right, so that is a quick highlight of batteries and corrosion. Stay tuned in the next one where we get to non-spontaneous electrochemical processes. Thanks for listening, be good, and I'll see you soon. Bye.